We are going to look at something that we will be using for the rest of the year. It does have to do with the sun. It also has to do with stars. It has to do with galaxies. It has to do with black holes. It has to do with a lot of stuff. Okay? This is very important that this topic goes into your brain, and it is something that you've probably never heard of before. I want to put that out there first, okay? What is this topic called, or what is it? It's known as black body radiation. And this is one of the most important concepts that astronomers have in figuring out how the universe works. Before we jump into it, I just want everybody to know that everything gives off light. Everything. The sun does, stars do, light bulbs do, but so do you. Every possible thing that exists in the universe gives off some form of electromagnetic radiation. If you've ever played a video game where they have infrared goggles that you can use to see better when it would normally be nighttime, that infrared is a type of light. Infrared is a part of the electromagnetic spectrum. And those goggles allow you to see that infrared. People's bodies, because of the heat that they generate, give off electromagnetic radiation in the infrared part of the spectrum. And infrared goggles can see that. So can some awesome animals like snakes. Everything is going to give off some form of electromagnetic radiation. Now, if you are a black body, these are hypothetical, these are theoretical objects that don't exist in the universe, but they are a very important way to describe an important phenomenon that exists in the universe. If you're a black body, just like anything else in the universe, you are going to emit your own light. Humans emit light, stars emit light, the earth emits light. It just depends what wavelength it is. You can absorb light. So if you've ever laid out on a beach, you've been absorbing ultraviolet. That's why you get a suntan. Everything that exists can absorb light. If you put French fries under a heat lamp, it's absorbing infrared light and it's keeping them warm. So everything can emit light. Everything can absorb light. Normally, things reflect light. That's why you can see objects, because objects are going to have, like a wall, it's going to have a light ray from a light bounce off of it into your eyeball. A mirror is going to obviously reflect light. Things reflect light, and that's why you can see them if they don't give off their own. Black bodies don't do that. There's no objects that exist in the universe that do not reflect light. You might think, well, what about a black hole? A black hole is actually a region of space-time that has extremely strong gravity. It's not an object. We're going to get to black holes later this year. But there's no actual object that does not reflect light. Even stars do reflect light. So the sun has starlight hit it, and some of that starlight is going to bounce off. Some of it's going to be absorbed, but some of it is technically going to bounce off. Now, for a black body, it does not reflect any of that light. It only absorbs light. So we're going to take the reflect off. If you are a black body, all right, these, again, don't exist, but if you are one of these hypothetical objects, you are going to absorb all of the radiation that is coming into you. So if you are a black body next to the sun, you're absorbing all of the radiation from the sun and not reflecting any of it. And then you are going to emit your own radiation. The black body does not reflect any light from anything else. It only emits its own radiation, which means when you are looking at a black body, the light that you're seeing from that object is only from itself. There's nothing that's bouncing off of it. The light that you're seeing from that object is only from itself. There's nothing that's bouncing off of it. Why is that important? Because it turns out that the temperature of an object is going to determine the wavelength of light that comes out of it. The temperature of an object is going to determine the wavelength of light that comes out of it. That's why you have infrared, because your body is at the right temperature to give off infrared light. The sun is hot enough that it can give off wavelengths in all parts of the spectrum. Depending on the temperature, you're going to have a different color of light coming off of something. Think of a fireplace poker. I know that you guys are in Florida, so most of us don't have fireplaces. You still know what a fireplace is. Think of what would happen if I left that metal fireplace poker in the flames. It would start off as black, and then as it heated up, eventually it would start to glow kind of red. If it kept heating up, then it would glow orange and then yellow, etc. So the temperature of that object is going to determine what sort of light is being given off. And we can measure that wavelength of light. We have these instruments called spectrometers, and they can measure exactly what wavelength of light is coming off of an object. And if we can compare what we see from an object to what we know it should be, we can actually determine how hot an object is without ever using a thermometer. We just look at its wavelength of light. I wonder if you guys can think of anything that's really hot, really far away, that an astronomer might want to know the temperature of without going there. I don't know. I don't know. You got me. But we can now measure the temperature of distant objects without a thermometer. We look at the color of light that's coming off, and that's going to tell us how hot something is. Here's another explanation for you.
Over 100 years ago, physicists were trying to figure out how things glow, like molten glass or hot lava. It seems like a simple question and was being pondered by such physicists as Lord Rayleigh at the turn of the 20th century.
I give you a wooden skewer that when touched to a flame glows orange-red.
Rayleigh knew that the color of this glow depends on temperature. Like the sun that has a surface temperature of 5,500 degrees Celsius radiates a bunch of different colors that together look white to us. Or me, at 37 degrees Celsius, I have this invisible halo of infrared light. Fun fact, infrared light is invisible to humans, but snakes can actually sense it from up to a meter away to detect prey. Rayleigh wanted to understand where the light came from and come up with a rule that would predict how much of each color it would emit. This is its spectrum. Another fun fact, Lord Rayleigh was the guy who figured out mathematically why the sky is blue. So Rayleigh thought of the simplest possible object, something that absorbs all light. Objects absorb, emit, and reflect light. Rayleigh's object would only absorb and emit, but not reflect. So all you would see when you look at it is its glow or its radiation. Physicists call this a blackbody. Technically, a blackbody isn't black, it's glowing, but whatever, physicists. A true blackbody doesn't exist in real life because nothing absorbs all light and radiates perfectly. Although stars like the sun come pretty close. Kind of funny, right? That the brightest thing we know in our solar system is the closest thing we know to a blackbody. Physicists.
Something important to note is that it is the peak wavelength that tells you the temperature. So if you're looking at an object that is 5,000 degrees, it's going to give off light in all of these different wavelengths. From all the way down here, maybe 250, all the way up to 2,500, but it peaks at just over 500 nanometers. Wherever it peaks, that is going to be what tells you the temperature. If it's not quite as hot, then it's going to be peaking at, let's say, 650 nanometers. You're going to notice that as it cools down, this peak actually gets longer and longer of wavelengths. The longer wavelength of visible light is red. The shorter length of visible light is blue. Now I mentioned that I had a fireplace when I was growing up, and if you let the fireplace poker in, it would start to heat up. This is a demonstration very similar. There's a nail that is connecting two copper prongs, and they're going to run electricity through this copper, through the nail, out through this copper. As the electricity is going through the nail, it's not very good at conducting electricity, so it's going to start to heat up. As we start to run electricity through and this nail heats up, it's going to start looking red, and we see there's some red light. As it continues to heat up, then we get more yellow, and then we would get more orange, and eventually, if you get all colors, it's going to start to look white. And unfortunately, this nail melts and stops the electricity from heating it up, so it starts to cool down, and we have a peak of orange and then a peak of red, and then you can tell that it's starting to cool down. Now, as it cools down and cools down and cools down, it's going to start releasing in the infrared part of the spectrum instead of visible light. Does that mean that you would not want to touch that nail? No, it's still obviously very hot. Even though it's not really giving off visible light, it's still giving off infrared light. We just can't see that. If we did this one more time, you're going to notice that the peak wavelength corresponds to the color that you see. It starts off red, and then you get red and orange, and then you get some yellow, and then you start to mix all the colors together. It starts to look white. That's why it's known as white hot, which is hotter than red hot. If it could have kept going without melting, eventually this peak would have been over the blue part of the spectrum, and the nail would start to look blue. Unfortunately, it melts, starts to cool back down, and it goes back through the colors in the other direction. In simple English, this is known as Wien's law. The hotter something is, the higher frequency of light it gives off. Let me repeat that because we're going to use that for the rest of the year. The hotter something is, the higher the frequency of light it's going to give off. One more time. The hotter something is, the higher frequency of light it's going to give off. And it comes with a very easy little equation. If you know the maximum wavelength, all you have to do is 0.29 divided by the temperature. You rearrange this, and the temperature equals 0.29 divided by maximum wavelength. That's very simple. It's one division problem, and you can basically figure out how hot an object is from millions or billions of miles away just by looking at the color of light that's coming off of it. This is a little graph that I can move around, and if I put the graph roughly what the sun's temperature is, you're going to see that the sun has a peak wavelength of about 500 nanometers. 500 nanometers actually is directly over green light. Is our sun green? Actually, yeah. Our sun's peak wavelength is green. Now, it doesn't look green because green is right in the middle. So the sun is actually giving off a whole bunch of all of the visible light, all of the parts of the spectrum in the visible range. If you see all colors of light, it actually, to our eyes, looks white. If you were in space and you were to look at the sun, please never do this, but if you were to look at the sun without the light going through our atmosphere, the sun looks white because it's giving off wavelengths in all of the different parts of the spectrum. So how do we know how hot the sun is? Because the peak wavelength is directly over this green color, and it turns out that if you have a peak wavelength directly over this green color, your temperature is about 5,700. If I make the temperature a little bit colder, this peak wavelength is going to move to the right, which means it's a longer wavelength. We would see that as red. So a red star is going to be colder. If we make the temperature hotter, well, the peak wavelength is down here. It's actually an ultraviolet. What is the most amount of light that we actually see from that star? It's blue. So the hot stars look blue to our eyes. If we could see in the ultraviolet, they would look extremely bright, but we can't. We can only see invisible light with our eyes. So they look blue because of all the visible parts of the spectrum, the hottest stars are giving off the most blue light. Going back to our sun, a cool consequence of our sun giving off more green light than anything else is the color of plants. When you think of plant life, most people think green. Think of a leaf or a flower or a jungle. It's very green. Why would plants be green if the most amount of light that comes off of the sun is green? Also keep in mind that in order to see something, light has to bounce off of it into your eyes. So if we are seeing the plant as a green plant, that's because green light is bouncing off of that leaf and into our eyes. So that plant is not absorbing green light. Why would the plants not want to absorb green light? Why would they want to reflect green light? Make a hypothesis. Turns out that if plants absorbed green light, the sun gives off so much green light, the plants would actually kind of get a sunburn and die. If a plant absorbed all of the green light that came off from the sun, it couldn't handle that much radiation and plants would die. So by reflecting green light, that plant has kind of put on like a sunblock. It's an evolutionary adaptation that plants have made to protect themselves from the sun. The fact that plants are green is another clue that this is correct, because our sun gives off the most green light of any other color. We don't see it as green, we see it as white because it's actually a mix of all colors to our eyes, and our brain interprets that as white. Quick recap, we use the color of things to determine the temperature of things that are far away. Super handy. And because we're going to be looking at things far away coming up for the rest of the year, we're going to be using this idea for the rest of the year. Keep in mind, though, that it's the light that the object gives off, not the light that it's reflecting. So if you're looking at a brick wall, can you tell the temperature of that brick wall based on the color of light? No, you cannot. It's only light that the object itself is giving off. Is that wall giving off light? Yeah, it's just not visible light. It's probably down in the infrared part of the spectrum. So if you had infrared goggles on, you could see that wall because the wall is giving off light. If you just look at the wall in your room right now, if a light bulb's on, you're seeing the reflected light from the light bulb. You're not seeing the light that the wall is giving off. And if it wasn't 2020, we'd all get to go out and look at the sun right now.